Myself, Dr. Vijayakumar, Associate Professor, Department of ECE, Aditya University. In this session, we will be seeing the temporal characteristics of random process. So, the temporal characteristics of random process consists of the correlation functions and covariance function. So, here we will see in detail about what is meant by correlation function and the properties of correlation function and what is meant by covariance function, and we will see the properties related to covariance function. And at the end of this lecture, students will be able to learn learning outcome 1, understanding the definition of correlation function, and in the learning outcome 2, they will be learning the properties of correlation function. And we will see the different cases for the correlation functions, like when do we say the random process is said to be independent based on the correlation function, when do we say it is orthogonal based on the correlation function definitions, and also we will be defining covariance function and correlation coefficient also. So firstly, we will be seeing what is meant by a correlation function. So simply, what is meant by correlation function means a correlation function measures the similarity in the random process. Okay, simply measuring the similarity in the random process. It will relate the random process itself at different time scenarios, and it will measure the amount of similarity between the same random process. That we call it as autocorrelation function. If it is between two different random process, we call it as cross correlation random process. So these correlation functions play a very key role in identifying the statistical dependence, memory, spectral properties, energy distribution of random signals. So it also helps in determining the noise characteristics simply by comparing the signals with the noise, and it also helps in understanding the memory of the random signal, correlation function. And correlation function is quite frequently used in design of filters, demodulators and receivers to match the original signal. So they will use a reference signal and they will see the collected signal or received signal. If it is matching, then we call it as perfectly received or 100% matched based on the correlation function. And correlation function and power spectral density are interrelated. We will see in the spectral characteristics of random process. So the correlation function is nothing but inverse Fourier transform of power spectral density. Both are Fourier transform pairs. So if you know correlation function, you can assess the power spectral density. So power spectral density is used in spectral domain, whereas correlation function is used for temporal characteristics. And correlation function is also useful in understanding the noise components, narrowband noise component, quadrature part of the noise component. So see here, correlation function is used to measure the similarity between two waveforms. The waveforms can be of same waveforms or different waveforms. For example, you can see A, D. Both are looking like a similar waveforms, okay, A and D. Okay, but the relation, see here, when it comes to origin, it is peak. At origin, it is in negative. So definitely they are 100% correlated, but the amount of correlation is in a negative way. Okay. And when it comes to graph, B and C are strongly correlated. Again, here the scenario is same. At the origin reference, you can see the negative peak. At the origin, you can see it is a positive peak. So both are 100% correlated, but the amount of correlation is negative. And whereas comes to E, E is no way correlated to any waveform. You compare AE, BE, CE, DE, the amount of correlation is very weak and the correlation value also will be very less. So the correlation function help us in identifying the amount of similarity between two functions or two waveforms. Okay. Waveforms pictorially, just by observing you can identify. When it comes to function, you need to use some mathematical formula for computing the amount of correlation. So already mentioned that the correlation functions are classified into two types. If correlation is computed between the same function at different time intervals, we call it as autocorrelation function. If correlation is measured at between two different random processes, I will call it as cross correlation function. Okay. So first we will see the definition of autocorrelation function and we will see the properties of autocorrelation function. Later on we will see the cross correlation function definition and properties of cross correlation function. So already mentioned that autocorrelation function means measuring the similarity in the same waveform at different time intervals. So here you can see the random process extracted at time t1, random process extracted at time t2. I am measuring the amount of correlation between both sample functions which are obtained from the same random process at different time interval scenario. So Rx of t1 comma t2 is equal to expectation of x of t1 into x of t2. This is the mathematical definition of autocorrelation function. Next, already we defined what is meant by wide-sense stationary random process in the previous classes. So here also, if you compute the mean and autocorrelation function is a function of time difference and mean is constant, then we call it as wide-sense stationary random process. For a wide-sense stationary random process, the representation will be Rxxx will be a function of time difference. Okay. In general scenario, correlation is a function of absolute time, whereas here wide-sense stationary, it is time difference. Okay. This is the mathematical definition of autocorrelation function, which is used for measuring the similarity in the same waveform at different time interval scenario. Now let us see the properties of autocorrelation function, very useful properties. So these properties will be helpful in solving the problems. Okay, solving the problems and assessing some parameters like power, energy, mean square value. You can see here first property itself, you can see x of t plus tau. Assume it is a wide-sense stationary random process. Now when tau is equal to 0, Rxx of 0 is equal to expectation of x square of t, okay, which is nothing but mean square value. It gives you the mean square value, okay, mean square value. If you want to compute, simply you can keep autocorrelation function with tau is equal to 0. And the second property is the maximum value of autocorrelation function will not exceed the autocorrelation function at tau is equal to 0. If you compute the autocorrelation function at any value of tau, it will not be maximum. So the maximum value will be at origin. Any value computed at any instant of time, it will be always less than the value at origin. So simply we can conclude that autocorrelation function at origin gives you the maximum value. Next, third property, autocorrelation function is an even function. So we know that even function, when do we say a function is even? F of minus x is equal to f of x. Similarly, if you compute Rxx of minus tau, you will get Rxx of tau. So using the formula expectation of x of t into x of t plus tau. Using this formula, if you compute, you will get the same. Rxx of minus tau will be equal to Rxx of tau. Clearly, autocorrelation function is an even function of tau. Next, fourth property, very much useful in solving the problems. Here you computed mean square value. This is mean whole square. So if a random process is ergodic with no periodic components, then limit tau tends to infinity, Rxx of tau is equal to mean whole square, provided random process have a non-zero mean value. So if random process is ergodic with no periodic components, limit tau tends to infinity, autocorrelation function is mathematically equal to mean whole square. Okay. And first property and fourth property will be useful in computing the power, energy, variance, mean, some statistical parameters. Okay, very useful properties. Next, fifth property of autocorrelation function. If random process x of t is periodic, so obviously autocorrelation function also will be periodic. We know that autocorrelation function is after all a function of random process. So if x of t is periodic, this also will be periodic. Next, if x of t is ergodic and has a zero mean and no periodic component, limit tau tends to infinity, Rxx of tau is equal to 0. This is a subpart of fourth property. In the fourth property, we have taken it as non-zero mean. Here we are taking zero mean. That's why its value is mathematically equal to 0. Next, seventh property, autocorrelation function of a random process cannot have an arbitrary shape. Why? Because we mentioned in the second property, autocorrelation function is maximum at origin and autocorrelation function obeys the even property with respect to tau. In the third property we have seen Based on second and third property, I can clearly tell that autocorrelation function will not have an arbitrary shape. It will have some specific shape which obeys the property 2 and 3. The property 2 is autocorrelation function will have maximum value at origin. Third property is with respect to tau, autocorrelation function have even values of tau. Okay, next. Random process, we have taken a random process with 0 mean and has a DC component A. Y of t is equal to A plus X of t. Then if you compute the random process autocorrelation function Ryy of tau, it will be equal to A square plus Rxx of tau. And similarly, random process Z of t is a combination of X of t plus Y of t. Rz of tau is equal to Rxx of tau, Rxy of tau, Ryy of tau, Ryx of tau. We will see what is Rxy and Ryx of tau in the cross correlation function. Okay. Next one is cross correlation function. When you are measuring the similarity between two different random processes, namely X of t and Y of t, here we have taken. If you are measuring the similarity between two different random processes X of t and Y of t, then we call it as cross correlation function. X of t is one random process, Y of t is another random process. If it is White's and stationary, clearly cross correlation function will be a function of tau. Next, properties of cross correlation function. Before proceeding to the properties of cross correlation function, we need to assume the stationary random process is White's and stationary random process. The first property is cross correlation function is also even property should be satisfied. Rxy of tau is equal to Ryx of minus tau. And the second property is, if you compute the cross correlation function, it will be always less than the geometric mean of Rxx and Ryy at tau is equal to 0. B is equal to square root of AC, something like that, geometric mean. Rxy of tau will be always less than the geometric mean of Rxx of 0 and Ryy of 0. And one more definition, same in a similar manner. If you compute the cross correlation value, it will satisfy the inequality. Rxy of tau will be always less than arithmetic mean of Rxx of 0 and Ryy of 0, A plus B by 2. C is equal to something, A plus B by 2. Next, fourth property. If X of t and Y of t are statistically independent and at least White's and stationary, Rxy of tau is equal to X bar into Y bar. So, when it comes to independent random variables, we know that E of xy is equal to E of x into E of y. In a similar manner, Rxy of tau is equal to X bar into Y bar. Next. If two random processes have 0 mean and jointly White's and stationary process, this is an extended version of fourth property. X bar is 0, Y bar is 0, obviously the product will be 0. These are some properties of cross correlation function. Let us see some sample problems by applying the properties of correlation function. Here the problem is asked something like this. Compute the variance of the random process X of t when autocorrelation function is mathematically given as Rxx of tau is equal to 2 by 1 plus 2 tau square. So, let us use the property 4. Based on the property 4, it is equal to mean whole square is equal to limit tau tends to infinity Rxx of tau. So, tau tends to infinity. So, 2 by infinity is 0. So, its value is equal to 16. Mu x whole square is equal to 16. From that, mean is equal to 4. Next, based on the property 1, limit tau tends to 0, E of x square of t. This is nothing but mean square value. So, when tau is equal to 0, 16 plus 2 by 1 plus 0, it is equal to 18. This is mean square value. Mean square value, that is mean whole square. Now, we need to compute the variance. We know that the variance of x is equal to E of x square minus E of x whole square. Using this relation, which will be equal to 18 minus 16, 2. This is nothing but variance. So, autocorrelation properties will be very useful in computing other statistical parameters like mean, variance and mean square value. Again, here also they are computing some statistical parameters. You can use the same properties. Okay. For example, see here, Rxx of t comma t plus tau is given. What is the first question asked? Verify whether it is first order stationary or not. How do you verify? Already given mean is equal to constant. So, clearly it is a first order stationary. Mean is constant, first order stationary. The second question is compute the total average power. Average power is nothing but mean square value, property 1. So E of x square is equal to limit tau tends to 0 Rxx of tau. So what you will get when you keep tau is equal to 0? 36 plus 25. Obviously this value is equal to 61. Generally power is expressed in watts. So here also power is expressed in watts. It is true. And we need to verify whether it is ergodic or not. So if it is ergodic, limit tau tends to infinity, Rxx of tau is equal to mu x whole square. Already we computed mu value is given 6. Now let us apply the property 4 and compute the mean whole square. What I got? 36. And already mean is given as 6. So 36 is equal to 6 square. So it is ergodic. Next, AC power. AC power is nothing but variance. So variance can be computed using mean square value and mean whole square. 61 minus 35. So but answer given is some other value, 36 watts. Obtained value is 25 watts. So the answer is wrong. The last statement, AC power is having a different value which is not equal to 31 watts. Next, one more important function which is very much useful and which can be related with autocorrelation function and cross correlation function, covariance function. Covariance function is a measure to degree which random variables vary together. So this is also something like measure of similarity, but here up to how much degree the random variables vary together. And the covariance definition is Cxx is equal to E of x minus mu x into E of x2 minus mu x2. Okay. So if it is auto covariance, same function, cross covariance, different function. So the properties of covariance, Cxx of T1 2 is equal to Cxx of T2 T1, symmetry property. And Cxx of T comma T is equal to variance of its value. Next, Cxx of T1 comma T2 is 0 means we can assume the random variables are uncorrelated. Okay. These are the properties of covariance. And one more important property, covariance, Cxx of 0 is equal to Cxx of tau is equal to 0. Cxx of tau is equal to 0 is equal to Rxx of 0 minus x bar whole square. So this is one relation. Cxx of T1 comma T2 is equal to Rxx of 0 minus x bar whole square. This is the relationship between covariance and autocorrelation function. So coming to the summary, what we have learned here, we have seen what is meant by correlation function and how it is useful in many applications, and also we have seen types of autocorrelation function, ACF and CCF, and also we have seen the properties of correlation and few problems related to properties of correlation. And covariance gives you how much degree the random variables are similar, and also we have seen the properties of covariance. Covariance and autocorrelation function are interrelated to each other. So in the next session we will be seeing the LTI systems, linear time invariant systems, and in the linear time invariant system we will compute the temporal characteristics like mean value, mean square value, autocorrelation function, cross correlation function. Okay, thank you.